when I was at varsity. And it's the book that is used in almost all institutions, just different versions. So it's a very old, established course. You participate, you will pass. You don't participate, you will have a problem at the end. When we do an assessment as a good student, please check your assessment. Don't wait. Up to now, we are still receiving emails of unmarked things in assessments of first semester. Don't wait for that. So let's just be disciplined and we get it done. The pass rate is around from 70 to 80, which is very good. So let's just participate. One thing I've noticed from you guys is when you are home, you don't look at it as a lecture. I could as well also relax in bed, switch off a video and listen like I'm listening to radio. It doesn't work like that. You have work ethics. You have to get yourself in the mood. Don't take things casually. Okay, as I said, I would sleep in bed in my pajamas and do what, but no, we don't approach things like that. Just take it as if you are in a lecture. Wherever you are, please have a pen and paper. It's very participatory. If you don't participate, you won't see how to draw the timing diagrams and all that. That is the first caution that I want to caution you. We will be drawing timing diagrams, and you have to draw, you have to understand what is happening for you to proceed well. Okay, what am I saying in short? You have to participate. When I tell you to do something, try and write something and see how the answer and participate and see what is going on. Don't just listen. It's not a matter of listening, you have to participate. Okay, we've got almost a quorum. Well, it's not a meeting. We can even lecture with one person. So I think we should start with our lecture. So the first chapter is Introduction to Sequential Circuits. Today we are going to go as slow as possible and look at section A. Okay. So, we've got two types of circuits, right? We have combinational circuits and sequential circuits. I can't see the topic here due to screen sharing. Let me just see if I can move it. Yeah, let me move it somewhere down. Okay. Now, a combinational circuit as being shown here, the output depends only on the current inputs. What is a combinational circuit? It's a circuit, electronic circuit, whose output depends on the current values of the signals applied to the inputs. It doesn't matter the previous order. The output depends on the current values. Look at this gate. This is the output, this is the input. If you have 0 and 1 here, the output will be 0. It doesn't matter what was there before. So that output is a function of the current value of the input. An example here, you say at home, if you had a TV channel that doesn't have up and down buttons, you people have not seen that. I'm sure you will say, well, how can you have a TV remote like that? They were there some 20 or so years ago. It does not have an up and down button. You just punch in the number that you want. They were there. So that is an example of combinational logic circuit. It doesn't matter where you are. Now, next, the next one is okay, I'm still admitting people. Okay, my slides were not. The next one is the sequential logic circuits. Okay, which one is this? This one consists of combinational circuits and storage elements. It has memory. We say the combinational circuit does not have memory. It just depends on what is at the input. A sequential logic circuit, once you take a combinational circuit and add on memory, then you get a sequential circuit. What are we saying? The output of the sequential circuit depends on the current values of the inputs and the past, some past information. There is and what happened in the past. An example, if we use the TV, is the TV channel with up and down buttons. If you are watching sports on 200, when you press up, you go to 201. What was the memory? The memory is the 200. That is the present state. Then you press up, you go to 201. So it has memory. And then the input is the pressing up. Then the output is the next channel you go to. So that is what we are saying here. Still, that is what we are saying here. That, sorry, I'm just dealing with. So that is what we are saying here about a sequential circuit. So you've got inputs, you've got memory, and then you've got outputs. It is basically has feedback. That is what this one is telling you. You have feedback. That feedback brings in the memory. So now let's define both of them. This is a combinational circuit. Those are the outputs that depend on the current values of the input. This one is a sequential circuit that has a combinational circuit. You've got n inputs here. You've got m outputs, and then you've got a feedback. You've got a feedback which has a memory unit. So that is this. That is the next state. That is the current state is fed with the input. The current state is channel 200. The input you pressed up to give you the output is the next state, which is 201. And that will be kept in memory as well to be the current state of the next action that you will do. Okay, so that is what we are talking about. So now, this is a summary of what we've been talking about. What is a state? The state is the contents of the storage elements. What is stored in memory? That is what the state is. The output is a function of the input and the current state. The next state is a function of the inputs and current state gives you the next state. Sometimes the output can be the next state. A sequential circuit is specified by a time sequence of inputs, internal states, and output. You must know the inputs, the internal states, and outputs. So this circuit has got n inputs, it has got m outputs, and it has got 2 to the power k states. Normally, the latches and flip-flops are the ones that store the states. So we're just defining what a combinational and sequential circuit is. So a combinational circuit has no memory, an AND gate. Whatever is at the input gives you the output. A sequential circuit has got memory. How are they made? A combinational circuit is just a combination of gates. There is no memory. A sequential circuit, there is memory. You've got flip-flops. Flip-flops are the ones that bring in memory or feedback. This one has got no feedback. This one has feedback. Feedback brings in memory. So the output for a given set of inputs is independent of the order in which these inputs were changed. The current inputs determine the output. Whereas a sequential circuit, it has memory. It's not only the current input. You have to factor in what happened in the past, the memory elements, the order of which the inputs change happened, and then that affects the output. So that is basically the definition and difference between combinational and sequential circuits. Okay, so now, next, I'll just introduce something that we all know here. By the way, if you have a question, you just raise your hand and then you ask. Okay, these slides are already on Moodle. The audio ones will be there by Monday for the rest of the semester. So we've got the clock. Sometimes sequential circuits, their changes occur at a particular time. The output does not just respond to the input at any time. Sometimes it responds based on a clock. So you've got a clock signal that does that. The The clock can be active high, it can be active low, can be level triggered or edge triggered. The cycle and all that, I won't go much into that. So, depending on the clock, sequential circuits can be classified or divided into two types. We've got synchronous sequential circuits that are clocked. The changes in output do not occur immediately when there is a change in input, but the next time there is a clock pulse. The output responds to the input at a clock pulse, mostly a clock edge. Then we've got asynchronous circuits. These ones are not clocked. The output, when the input changes, the output tracks the input. It is not clocked. That is the difference. Synchronous and asynchronous sequential circuits. Some are clocked, others are not clocked. So, the building blocks of sequential circuits, of course, we've got the gates, the normal gates. But where does the memory come from? The memory comes from what we call latches. That is an asynchronous sequential circuit. It doesn't have a clock. It operates with signal levels rather than transition. They are level sensitive. And then what is the difference between latches and flip-flops? Flip-flops are clocked. The output only is allowed to respond at a particular edge of the clock. They are edge sensitive. Actually, flip-flops are made from latches. They are made from latches. Okay. So now, the first latch, you've seen that. That one is an SR latch. It's NOR-based. During my times, I used to find it difficult. Why start with R here, S here, and Q, the main here, and Q complement here? But it's done that way for you to understand properly. So you've got your set, you've got reset there, and this is your main output, Q. Now, we've got a functional table. You've done that. Remember, this is supposed to be the complement of Q. Can you just draw that table? Nobody is looking at you, or you can show me, you can share your screen after that, and give me these values. Are we together? I'm giving you 2 minutes to determine the value of Q and Q complement when S is like, when the value of S and R are as given. Can you do that? Okay, it's you now. And then one of you who has guts, you can show me what you have done, and then we will use your functional table. So can you do that? 2 minutes. You can even go further and tell me the behavior of that circuit for the combination of the inputs. Let's go for it. 2 minutes. Oh, you will need that. Let me upload it. Okay, just do it. If you come here and sit and think that, look, you will just listen, no, you have to participate. We are going to draw waveforms, and waveforms, you can even have notes with you. You will have notes with you, but if you don't understand, you won't do anything. You just have to understand. And this is the first thing. You might not be willing to do anything, and you expect that miracles will happen further there. So can you do that? When we discuss the answer, I will wait for one person to show me what they have done. And then when we discuss it, you will be checking with yours. So can you do it? 2 minutes. So that is therefore you are reading. Let's fill in the table. Okay, what did he say? Now, if you don't have time, you know that this is an OR gate. In an OR gate, which one fixes you is a 1. So deal with the cases. where you have a 1, I'm just looking at the shortest way to deal in. You can fill compulsory things. For example, if S is 1, 1 with anything will be 1. If you pass it through a NOT gate, it will be what? 0. So anyway, whatever happens here, if S is 1, Q will always be what? Q complement will always be 0. The easiest way. So you can go anywhere here and check where S is 1. Q complement will always be 0 and fill those places. I'm showing you the shortest way to do it. If R is 1, Q will always be what? 0. If you go, R is 1 here, Q will always be 0. So you can fill those ones in and start filling in the others. So we've said if S is 1, Q will be 0. If R is 1, Q, so you can fill in that and that. Here S is 1, okay? We've said Q complement will be 0. You'll have filled in that, and then you can fill in all, you can go through the circuit and fill in all the combinations. Now I will ask a question. Is there anybody who couldn't fill in that? What we are saying is if S is 0, R is 0, the value of Q and Q complement will depend on the previous. That's why they say it's in memory. When S is 0, R is 1, Q will be 0, Q complement will be what? 1. If S is 1, R is 0, Q will be 1, Q complement will be 0. That is set. The previous one was reset. And if they are 1, 1, Q will be 0, Q complement will be 0. We don't want this condition. That is why we say it is undesirable. We want this to be the complement of this. That is why we say it is undesirable. It doesn't mean that we've got no signals there. We've got a 0 and a 0, but we don't want it. It's an undesirable state. That is our first welcome to the world. Is there anybody who has a problem with that? And something funny, the students who keep quiet are the ones who have a problem and are the ones who fail, and they are the ones who complain at the end, and are the ones who, I don't know what happens to them at the end. If you have a problem, just let us know. Now, I just want, for the sake of students who want to expand their knowledge, I prefer going into something. Why do we say we don't want that state? Why is it undesirable? Okay, it leads into a condition called metastability. Now, I want you guys to apply your mind, and let me give you the condition. It enters into a metastable state when us and let's look at this. This is our circuit. We know how it behaves. What happens when S and R go negative at the same time, and these delays, the gates have different delays. I just want a student to apply. If gate 1 is faster than gate 2, what will be the value of Q? Initially, Q and Q complement, assume initially they are all 0, 0. And S and R goes to 1 at the same time. And gate 1 is faster than gate 2. What will be Q? I will need an answer there. This is initially 0, 0. This and that go to what? 0. They were 1. So they are now, this and this are now 0. This is 0, this is 0. So if this gate is faster, that 0 here will be here. That one will be 0. Q will be what? 1. So we will get that. Anybody with a problem with that? Now, if this gate 2, is faster than gate 1, the propagation delays here are faster than the delays here. So you had 0 here. This one went to 0. So 0, 0 gives you what? A 1 here. Then you've got a 1 and a 0. It will give you what? A 0 here. 1 and a 0 will give you a 0. That 0 comes here. 0, 0 gives you a 1. 1, 0 gives you a 0. In this case, Q is 0. So you don't want such situations in a circuit. You don't want, when you don't really know, you cannot have a chip or gates with the same propagation delays. They will definitely be different. So you don't want a situation whereby you don't know whether this Q is a 1 or 0 depending on propagation delays, when some conditions, some hazards in the circuit happens. So these are metastable states and we don't want them. That is why if we go back, we say we don't want a situation where Q and Q complement are at the same value. Those are the undesirable states that we don't want. That is why we don't really like latches. They have these problems, metastability of the output depending on the conditions, the delays in the gate. So that is why we've got what we call undesirable or metastable states. Okay, now, if most of you have seen the way I set my questions, I prefer design type questions. I don't like questions where you memorize things. And this one, I will never ask you how does an SR large function? What is an SR large? You will not get that. You will use it. These tables, that like the function table that is here, is on your question paper. No need of memory. Now, we've dealt with an SR large. These are the timing diagrams. Those are the questions you get in the exam, the time, how you know the functionality. So this is your S, this is your R. Can you draw the graphs of Q and Q complement? Please do it. Giving you 3 minutes to do that. With that, I need, so you will see from here, from time 0, S is 0, R is 1. What do you expect to be the value of Q and Q complement? Remember, don't wait for the answer. Don't. All my courses are almost open. If you don't understand, you will have a problem in the exam. Just draw that. We have started. All of you have got 100% now. Don't just sit there wherever you are and do nothing. Can you draw those graphs and give me what Q and Q complement is? And for the sake of the next lecture and in the future, you can print this and draw on top. It's actually quicker. Okay, so those are 3 minutes. I'm timing myself. Let's go for it. I can start explaining now and check and confirm your answer. Now, this is the sign of your SR large. Actually, this is called set. It sets Q. This is called reset. It resets Q. When you see signs like this bubble means negative. It means is active high. When you see that it's active high, this one means the complement. You know what active high means. I'm just trying to give people the rule of the thumb. So this one is active high. So when S is 1, it sets the large. When R is active, which is 1, it resets the large. And that is what the table says. But when both are 0, 0, it is in memory. It remembers whatever the previous value of Q and Q complement remains. 0, 1, we said it's active high, so the reset is the one active, it resets Q. Q is the reference. When S is 1, when set is 1, reset is 0, it will set Q. Q is the reference. That is why we're saying it sets the large, resets the large, previous. And when they are both 1, 1, we saw because of the NOR gates, the output will be 0, 0, and we saw we don't want that state. It is undesirable. It will give us problems. So now let's go through this together. The set is 0. The reset is 1 from 0 to T1. What will be Q and Q complement? Reset is active high. So what do you expect here? So it should be reset. Reset means Q should be reset 0 and the complement 1. Now, let's look at T1 to T2. The set is what? 0, reset is 0. 0, 0. It means it is in memory. So at this point in time, from here to there, while you've got 0, 0, it is in memory. So the previous 0 value that was here will remain from there to there. Okay, I didn't want to show you that. You can check that on your answer. So we said set is 0, reset is active, it will be reset. When we say reset, we are looking at the Q. This is the complement. So Q will be 0, this one will be 1. T1 to T2 is 0, 0, 0, 0 in memory. Whatever value was there before will be kept there. T3 to T2 to T3, the set is active, reset is inactive, so the flip-flop will be set. That is why here it is set, and the complement will go low. T3 to T4, they are both 0, 0, so it is in memory. 0, 0, it is in memory. Whatever was here will remain, whatever was here will remain. T4 to T5, set is 0, reset is active, which is 1, so it will be reset. So that goes to 0, the complement goes to 1. T5 to T6, set is active, reset is active. They are 1, 1. Are you getting that? That they will show 0, 0, but we don't want that. It's an undesirable state, so both will be 0, 0. T6 to T7, reset is active, set is inactive. So it will be what? Reset. We look at the Q, the complement will be 1. From now on, I will only be dealing with the Q. T7 to T8, they are both 0, 0, so it will be in memory up to here. T8 to T9, set is active, reset is inactive, so it will be set. T9 to T10, they are both what? No, set is high, reset is high. Here they are both high. So it will go to 0, 0, our undesirable state. 0, 0, undesirable state. We said anything can change in an undesirable state. Now, this is our condition where they are both 1, 1 in an undesirable state, and then they both go to 0 at the same time. This is what we were looking at. So we said in that incidence, the output will depend on the gate propagation delays. Any question there? Anybody who got a wrong answer and they don't understand why, you can send me a chat or you can talk. Just unmute yourself and talk. Is there any problem before we move on? Just mention the times, between time what, time to time what. I didn't get it right. Anybody with a problem? Okay, I'm assuming there is no problem. You've got an option of sending me a chat, or you can just talk. You are alone wherever you are. I'm assuming you don't have people looking at you. So just feel free and talk. Okay, so that is the SR latch. Now let's move to another one. This one is called the SR NAND latch. It's the negated latch. Here is the function table. Can you determine for me the function table? I'm giving you, this is blocked. That is your S bar, R bar. You've got those values. Can you determine for me Q and Q complement? Please attempt it. It is an AND gate, so 0 rules. You should know that. Nor 1 rules. and 0 rules. So start with those values that have zeros. They will fix the other outside. So quickly, let's get the function table of that. And then you will tell me which one is memory, which one is set, which one is reset. Remember, the set complement is up, the reset complement is down. Can we get it? Three minutes. Okay. Unless if somebody wants 1 more minute, I think our time is up. Remember, this is the basics. So don't move with the problem. It will keep on getting bigger. So if you have a problem, let us know. So this is what you should have. Remember, here is an AND gate, 0 rules. If you have 0 here, whatever this is, that will be a 0, Q will be a 1. So I would use that and say, if this is 0, is 0, Q will definitely be 1. And write that 1 here, put a 1 here. It's the shortest way of doing it. And then I come here and say, if R complement is 0, whatever happens, whatever comes in here, Q complement will be what? A 1. 0, 0, I have a 1 there, 1 there, and fill in the rest. And then I will say, if they are both 1s, if they are both zeros, this is 0, that's 0. Whatever happens, this will be 1, this will be 1. They are both the same undesirable state. And you can easily see that this will be set, this will be reset, and this will be the previous. You should have gotten that. Whoever has a problem, you can raise your hand. That is the logic symbol of the SR NAND large. Remember, you have these negations here. That is QQ complement. If these inputs are negated backwards, you get the first large. The behavior becomes like the first large. In short, if you take an as, pass it into a node, that the behavior is like the first SR large. It becomes the same as the NOR large. Okay. So now we've seen that we've got a problem called metastability. We've got undesirable states. When things change in a particular way, we can get into problems resulting in propagation delay. We don't need a circuit that we can't control. So how do we solve that problem? The easiest way of solving that problem is to start introducing an enable or a gate. This is the circuit you had previously. The SR NAND large, you've got the function table. So I'm just picking that, and then I've got my S and R, and then I've got my enable C there. So can you determine for me the function table there? We know that, let me just give you a hint. If the control is 0, if this is 0, that is 0, 0 rules, okay, 0, 0, that is definitely 1 and 1. Then we said for a NAND large, if this is 1 and 1, what happens there? So continue. Reason that when that is 0, you don't need different combinations of this. So what will be the next state? And then after that, you have when it is 1, it will depend on the others, on S and R. Can you please make sure you do this? Remember, we are adding something. So you have to get the function table. It is getting more and more complicated. We are adding some more functionality. So our 3 minutes, it's even a shorter one. So let's take 3 minutes. Let's get the function table. We have added an enable. Anybody who needs more time? Anybody who needs more time? You should have found that when that is 0, doesn't matter what happens there. This will be 1, 1. If that is 0, that will be 1, 1. And then there will be, you have that state, no change. If these are zeros, if this is 1, it's not really affecting that. If these are zeros, then you will have 1, 1 here, then you will have no change. Okay, so 1 enables that. Once you have 1 there, it starts behaving like an SR large, NOR large. So it is set when S is 1. Okay, when R is 1, it is reset. And then they shouldn't all be 1, 1 as we saw, indeterminate or undesirable state. So an SR latch is sensitive to its inputs at all times. It may be modified to be sensitive to these inputs only when an enable is asserted. So the circuit behaves like the SR NOR latch when the enable or C is 1. It retains its state when C is 0. We have added some bit of control. Now, this is more important. Can we do that? That is the symbol for an SR latch with enable. Remember, they are active high. Even the enable is active high. That is your Q and Q complement. That is the function table you've been deriving. So can we draw these state diagrams and determine the behavior? You need to find Q and Q complement. If you have something you are not understanding, you talk or you send me a message, a private message, if you don't want other people to know about it. So can you draw that? It will show that you are understanding what we are doing. 3 minutes is 9:35. 3 minutes, please. Anyone needing more time? Are we waiting for the answer? Okay, we will, as I said, this you have to understand the functionality with notes and what. If you don't know how, nobody will bring the same waveform. The waveform will definitely change. So please, you must understand what will be going on. Okay, so now let's check here. If you check carefully, when the clock is 0, during these points of zeros, 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 it will be in memory. That's the first thing. When the clock is 1, it behaves like a set reset large, which is active high. So let's start here. The clock is 0. Whatever you started with will remain. Then it goes high. It is enabled here. The reset is 0. The set is 1. So it will be set. When we say set, we are looking at Q. Q should go to 1 here. Then when it goes here to here, it is 0. So Q should remain 1. Doesn't matter what happens here. Then when you come here, it is enabled. It goes and checks. R is high, set is low, so it will be reset. So the Q should go low here. From here to there, nothing. It keeps memory, it's low. Keeps memory, it's low, up to here. When during this point and that point, this is enabled, it is 0, 0, it is in memory. So it will be in memory here. Then here up to here is the memory because of the enable. Then here it is enabled. Set is 1, reset is 0, so it will be set up to here. Up to there, it is in memory. Here it is enabled, there are 1 and 1. We said 1 and 1 is undesirable, but actually the actual output is 0. But we don't want both to be what? 0. So that is what happens up to here. And then once it goes low, it is in memory. But because that was undesirable, the memory, you don't really know what it is. But we actually know what it is. It is a 0. But we don't want to even deal with a situation where both are the same at the same time. We don't want that. Is there anybody with a problem there? Any question? Any comment? If you have anything, just send me in the chat. Now, the next one, we don't want If you don't want, I just want to ask students who like thinking out of the books. We don't want a situation where S and R are the same. We are getting an indeterminate, undesirable state. If we want to stop that, what do? I need an answer. If we want to stop S and R being equal, what do? I'm waiting for an answer from a student who is following and thinking. We don't want S and R to be the same. What do? It's an undeterminate, undesirable condition. What do we do there?
Would you add an inverter?
Yes, that's a very good answer. You connect an inverter there and have one line. S and R will never be the same if there is an inverter there. Thanks, Yashil. So that is what has happened. Same is the same diagram, the same here. But we have just done what Yashil has told us. There is the inverter that he talked about. And then we get what we call a D latch. That is a D latch. We've just made sure that the S and R are not the same and they are connected to D through an inverter. That is what has happened. Now you've got D. D feeds the S and then it feeds the R. Now, can we get the function table here? I'm giving you, this should be strictly 3 minutes to give me the function table. You've got C, which was our enable. And then you now have the previous S and R's are connected to D. So we've got only one input, D, and the control. What will be the next state? Build from what you've been looking at. So I'm saying let's get the function table here. Just follow what we've been doing and tell me how the behavior of that circuit is with the function table. 3 minutes. It's basically, when C is 0, we saw that it's in memory, no change. When D is 1, D is connected to the set. We said it will be set. When D is 0, Q will be 0. So that is what we call a D latch, a transparent latch. Transparent is when enabled, whatever value enabled when C is 1, whatever value is at D will be seen here on Q. Q mimics D when enabled. If D is 1 when enabled, when C is 1, C is 1 here. If D is 0, Q will be 0. If D is 1, Q will be 1. And we are looking at Q, not Q complement. And that here is the sign of the latch. That is D. That is C. It's active high. That is Q. That is Q complement. It doesn't have those problems of when they go together at 1 and all that. So we've just been improving. So the D latch eliminates the undesirable condition of SR latches. It ensures that S and R are never equal to 1 simultaneously, like we were told, by negating there. The D input is sampled when C is 1. So it holds the data in its internal storage. The D input is only checked when C is 1. If C is 0, it is in memory. That is the memory we are talking about, memory elements. The output, Q, follows what is happening at D, as long as the control input is gated. Okay? So the circuit is actually often called a transparent latch. It's transparent. When enabled, whatever is here can be seen from the output. Okay, this should be a quick one. you can say nobody will ask you what a transparent latch is. They will give you its functionality. You should know the symbol, but you will get waveforms. In fact, we used to have a test after every chapter, and this part is just waveform analysis. So can you quickly, 3 minutes, go through this? That is how it behaves. Don't memorize that. You will be given. So you've got the, if you check carefully, that C is becoming a clock. So don't worry when I've written here a clock. This is C, not clock. But C becomes a clock. We are moving towards flip-flops. Then you've got your D. So can you give me what Q is? 3 minutes. Okay. Hello. Can we now look at it, all of us? Or you still need some time? Okay. We will explain what is happening. That this is what we call a D latch, a transparent latch. Whatever is at D goes through, is seen at Q when C is high. C is becoming a clock. And this is actually a true complement here. We don't have the undesirable state. So without looking at the answer, we are only dealing with Q, because Q, this is a complement. So you've got D. C is 0. When C is 0, it is in memory. Whatever happens at D doesn't affect the output. So even if D is changing here, it doesn't matter. If Q was 0, it will remain 0. But now, when it goes high, during T1 to there, it is transparent. Q will be the same as D. So you expect here, Q should be high. From there to there, it is in memory. From here to here, Q should be like D. So Q should be like here. From there to there, it should be in memory. So Q should be continue to be 0. Once it reaches here, it should be like D. So it should go high. D is high. And it should go low. Remember, it follows, not that. It is transparent. If D changes when enabled, Q should change. What I'm saying is transparent Q. When enabled, Q is what D is, follows. So D is initially high, so Q will be initially high. D goes low, Q will follow it until here. It won't follow it here because it is disabled. Until here, then it will follow it until there, and then in memory. So that is what you expect to get. Anybody who has a problem with that? And that is the timing diagram. These are the kind of things you are expected to do here. And you will not only get one. You should go and check the tutorial. You will get a combination of 3 or 4. If you fail the first stage, the second stage is normally not good. So today, what have we looked at? A summary of what we have done. You've got the SR latch, the NOR latch, the NAND one. NAND latch, these are the symbols. And then the D latch. The D latch, we said, is the SR with the control negated. We've seen how they behave. We've looked at their timing diagrams. So we've looked at the D latch. So this is what we have done today. And you should know their operations, and you should know how to draw the timing diagrams. So that is what I wanted to share with you today. But I'm just telling you that go on your website, look at the tutorial. We don't set one thing. It's a combination. That tutorial is the assignment is very comprehensive. Go look at it, and then after we finish next week, we are going to the flip-flops. Okay, people are saying we should, who still feels like we should do the D? Anybody who says we should repeat? Any other person? I've seen messages saying we should repeat the D example. We'll have to repeat it. We are here to try and understand. Don't just move without understanding what is going on. Okay? So I will share the D example. Okay, pay attention, please. Pay attention to what is going on here. The timing diagram. You can't solve a timing diagram before understanding the functionality of something. This is our transparent D latch. In simple terms, when C is high, it is active high, the value of Q is the same as D. In another language, if C is low, it is in memory. Whatever was there in Q is kept. People were saying we should repeat, pay attention. You have to understand something before you apply it. So the first step is to understand this. When C is low, there is no change. It is in memory. When C is 1, it is enabled. If D is 0, Q is 0. If D is 1, Q is 1. Simple, it's transparent. So you come here. The clock is our C. That C is becoming a clock. Later it will be a clock. So that is our C. We said when C is 0, whether there is a change on D, it doesn't matter. Whatever was there is kept. It's in memory. If it was 0, it will continue 0. But when it becomes 1, Q follows D. So from here to here, you expect Q to do what? To look like D. So it will be 1. From here to here, it will be 1. In short, in these instances, Q should have the same value as D. So that is 1. When C goes low, it is in memory. So it was 1, it will be in memory up to there. Goes high, it looks like D. D is 0, so it looks like D. C goes low in memory. C goes high, looks like D. Remember, D goes up and goes down. So it will follow. Not D goes up. D was up, then goes down. So it will go up because it was low. Look like it and come down. Up to here, it is in memory up to there. There is enabled, follows D. D is down, then goes up to there. And then from there, the enable is low, it stays in memory. So that is how the transparent latch operates. Any questions? I'm taking questions. Anybody with a question? Okay, if there is no question, we will stop there. We've taken about 1 hour and something. 1, our modus operandi will always be the same. Okay, I don't miss any lecture or anything unless I tell you, especially the double lecture, we will be having a double lecture. The Monday one is normally a tutorial. So next Monday, if you have questions on this, some people are even entering the chat now. Good luck. Now, next Monday, we will actually go through this, not go through, is a tutorial session to master what we have done today. Next Tuesday, we will be looking at flip-flops. I'm going to upload oral presentation. Just stay disciplined, attend lectures. And another thing, sign the attendance register. You are about 61 students. The rest are not attending and they will start complaints. When there is a problem, we go back and look at an attendance register to see, was the student attending? Believe me, if you attend lectures and the lecturer checks the attendance register, the approach they deal with you differs. You get a very receptive lecturer. He says this student comes to class, so the lecturer relates to you. If you come and they check the attendance register is 000, especially so me, the mood is different. Are you getting that? So sign the attendance register. It's important for us. It's important for you as well. If there is no question, go through these notes. By Monday, the audios will be uploaded. Okay. So by Monday, and then after that, we will continue the same. If there is nothing, I'm being called for other meetings. Let me just join. Okay. So let's meet on Monday. If you have a problem, anything, just email me.